Hello everyone. In the previous video, we have understood phenol is able to show electrophilic substitution reaction, and electrophilic substitution reaction will happen only on ortho and para position of the phenol, not on meta position. Like this is phenol and I am going to react it with CS3CSCl methyl chloride and AlCl3. In this condition, CH3 positive will be an electrophile. It's an electrophile looking for electron. For electron, obviously it will attack on benzene ring, not on oxygen, because oxygen will not give electron easily to it, because oxygen is highly electronegative atom. So carbon it will prefer. Which carbon? Ortho and para. So either it will attack on this or it will attack on para position, this one. So two products are possible here. If it is attacking on ortho position, ortho hydrogen will be substituted. This hydrogen you can check is substituted by CH3, and this hydrogen will eliminate out as H positive. Similarly, this is ortho substituted product. One more product is possible. CH3 can attack on a para position. So para substituted product with the release of H positive. Obviously when bond will break between hydrogen and carbon, electrons will transfer toward carbon due to higher electronegativity of carbon, and this hydrogen will release out as H positive, which I have released here. And these electrons, this carbon will use to make bond with CH3. This one. Now the question was in front of us, why not meta position? These are the meta positions. Why incoming electrophiles are not attacking on meta position? Let's check the reasons. There are two reasons for it. Number one, resonance of phenol. And number two, stability of carbocation generated after attack of electrophile. Due to these two reasons, incoming electrophile is attacking on ortho and para position, not on meta position. Let's discuss them one by one. First, resonance of phenol. For this, obviously we need to draw a resonating structure for phenol. This is our phenol. Let's start its resonance. Resonance means movement of the pi electrons. We know how resonance will come here. This lone pair oxygen will shift here, due to which one electron will be transferred toward carbon and one electron it will keep with itself, and bond will generate. Because these electrons are coming here, these pi electrons will feel repulsion and they will shift to next carbon like this. This is the first movement. Next structure generated will be this. When these electrons will shift on this carbon, lone pair will generate. Now in this lone pair, one electron is extra, this one. That's why this carbon will get negative charge -1. And this carbon is going to make double bond with oxygen, because oxygen has given electrons for the bonding. Now out of these two electrons, one electron it has transferred completely toward carbon, this one, and one it is keeping with itself. Because it has transferred one electron completely toward carbon, so what charge it will get? +1 charge. Because it has lost one electron and it has transferred it to carbon, due to which these pi electrons feel repulsion, and that's why they shifted to next carbon like this. Now next movement, very easy. Continue. Now these lone pairs will come here for bonding, and these pi electrons will feel repulsion and they will move to next carbon like this. Please have a very good command on resonance when you are dealing with aromatic compounds like phenol, haloarine. Next structure will be this. Pi bond will generate here and lone pairs will come on this cover. Now next, again these lone pairs will be shifted here for bond formation and pi electrons will move to next carbon like this. Pi bond will come here and lone pairs will come here with a negative charge. Oxygen will remain as it is, no change. And then finally this lone pair will come here and the pi electrons will go back toward oxygen like this. So the new structure will be pi bond will come here. Now here single bond will left. You can check because second bond has broken and electrons are shifted back toward oxygen. Now oxygen will have two pairs and obviously its positive charge will finish, because that positive charge was due to shiftage of this electron toward carbon. But now you can check oxygen got its electron back, so its positive charge will finish. So this is a first time resonance, clockwise resonance you can watch. Electrons are moving clockwise. Now if you have to draw resonance again, what will happen? Again oxygen will give electrons like this and now pi electrons will move like this, anti-clockwise direction. Lone pair will come here. Again double bond will generate between oxygen and carbon and oxygen will get a positive charge. Rest molecule as it is. Now again same, for bonding they will come and these pi electrons will shift to next carbon. Lone pair will come here, negative, pi bond here, pi bond as it is, oxygen as it is. Next movement, again in bonding, pi electrons will feel repulsion and they will go for next carbon. Next diagram will be lone pair here with a negative charge, oxygen as it is with a positive charge, and the last movement this lone pair will come here, pi electrons will shift back toward oxygen and this structure will be generated like this. This is a complete resonance of the phenol. You can check clockwise as well as anti-clockwise. Now due to resonance you can check electrons are present in the form of lone pair on which position. First is oxygen. You can check oxygen have a lone pair, but oxygen will not give its lone pair to electrophile as I have told you earlier, because oxygen is highly electronegative atom, 3.5. It will not give its electron easily to electrophile. Second option, carbon. You can check carbon have electrons and which carbon have electron most of the time. You can check this carbon, ortho carbon. You can check lone pair is available, ortho position. So easily electrophile can attack. Suppose here we have electrophile. What electrophile wants? Electron. Easily it can attack on this position. Another position you can check this carbon, para. Para carbon have a lone pair which can be attacked by electrophile easily. Next position again check ortho. This is ortho position. Electrons are available. Okay, check here which position? Ortho. On ortho position electrons are available. Check again which position? Para. On para electrons are available. Next structure you can check ortho. Which position electrons are available? Ortho position in the form of lone pair. So during resonance you can check electron density is increased on ortho and para position. That's why electrophile will prefer to attack on which position? Ortho and para. On meta position, you can check electrons are not coming. This is meta position, this is meta position. Check. Does in any structure the electrons are coming on meta position? No. Electrons are always coming on ortho and para positions. That's why electrophile will prefer to attack on which position during electrophilic substitution reaction? Ortho and para. Now, second reason in next video. Thank you.